Hello and welcome to lesson 8.6, Intersections of Planes. We're going to first investigate how two planes can interact in 3 space. So as you can see in the left option, you have infinite solutions. Because those infinite solutions form a line. You can have no solutions, because the both planes do not actually intersect, they're parallel to each other. Or you can have infinite solutions, because the two planes are exactly the same, and therefore form a plane. Now you can tell this just by looking at normals of the planes. So let's call it 2 of these normals, normal 1 and normal 2. For all these planes. So here, in the first instance, you can see normal 1 does not equal normal 2 in any format whatsoever. In the second instance, normal 1 could be some kind of scalar multiple of normal 2. But you'll also notice that the d values are not the same multiples. So k is some real number. But in our third case, the normals do seem to be some scalar multiples of each other, and so do the d values. So, what I suggest is we take the two planes, call it plane 1, pi 1, and plane 2 as pi 2, try to eliminate one variable, and use the remaining information to determine how the planes interact. If you can eliminate most of the variables, then there might be a possibility that you have the normals being exactly the same. If you can only eliminate one of the variables, then most likely the normals are completely different, and you'll be able to find a line of intersection. So let's take a look at this. Notice that these two planes' normals are completely different. They're not even scalar multiples of each other. So I'm going to take plane 1, and I'm going to actually add plane 2. What this will do is it'll eliminate the z values from this. So this is going to give me 7x minus y minus 8 equals 0. Well, what you can notice now is I can actually solve this in terms of y. So I get negative 7x plus 8, or y is equal to 7x minus 8. So this will allow me to actually come up with parametric equations that I can possibly use. So if we let x equal our parameter t, then y becomes z t, 7t minus 8. And in order to find our z value, all we have to do is substitute it back into one of our original equations. So substitute it into pi 2, we get 4t minus 2 times y is now given by 7t minus 8 plus z minus 19 equals 0. I'm going to first simplify. So 4t minus 14t is negative 10t, plus 16 minus 19 is minus 3, plus z equals 0, or z is equal to 10t plus 3. And there we can see that we actually get a line of intersection. which is most likely what we would have seen because these two normals are completely different. So we got our values for x, y, and z. Now, it is necessary to examine the normals of each plane, since it is possible for planes to intersect, to be parallel, to be coincident, or in any form. You need to investigate whether they're coplanar. So how you investigate whether three planes are coplanar, you have to investigate their normals and to be coplanar. Three vectors are said to be coplanar if one vector can be expressed as a linear combination of the other two. And you can check this by seeing if n1 cross n2 dotted with n3 would equal 0. Now, it's key to note that you have to actually work out the cross product first, just like you would for any cross product and dot product expression. Also, it's also key to note, doesn't matter which normal you use to start with as your second normal and which one's your third normal. So let's investigate some possibilities of ways planes can interact in three space. Three planes. So these are three instances of what are called consistent solutions. The first one has one solution, or one point of intersection. The next two have infinite solutions. The second instance has infinite solutions in the form of a line, and the third one has infinite solutions in the form of a plane. For the first instance, you can notice the normals, one coming out, one going this way, and one going this way. Are not related in any form. So normal 1 dotted with normal 2 crossed with normal 3, let's say, does not equal 0. Whereas if you take normals 1, 2, and 3 in our second instance, they can all actually lie in the same plane. Moreover, in our last instance, all the normals actually turn out to be collinear with each other. So they're even more so. So in that case, you only have to investigate whether they're collinear to each other. And just looking at the normals could help you out. Now there are three other instances of how planes could interact. In our first case, you have no solutions because you have parallel planes. In our second instance, we actually have two lines of intersection. This we consider as no solutions because it's not the same line. Two different lines. And the third instance, again, we consider no solution because you have three different lines. Again, the first one is easy to notice because the normals all head in the same direction. So they're all scalar multiples of each other. Easy to tell. The other two, you can see two of the normals head in the same direction. With the third one being coplanar. third instance, you can actually just determine or see, it's very similar to their one with infinite solutions, that these normals are again coplanar. So they all fit within the same plane. So first thing you have to do is investigate the normals to see what kind of options you have. And again, with three planes, you must eliminate one variable using, let's say, the first two equations, and same variable from two other equations. So I suggest 1 and 2 and 1 and 3, but technically it doesn't matter which two you use and which other two you use, as long as they're not the same two. Then you use your new equations to eliminate another variable from these, and determine your result from your solutions. So let's say an example of this. So first off, let's take a look at these equations. Let's call our first one 1, second one 2, second one 3. Well, you'll notice normal 1 is 1, 2, 1. Normal 2 is 1, negative 3, negative 1. And normal 3 is 2, 1, and negative 1. Just by inspection, you can see these are not non-collinear. So, going back, this turns out that it's not no solutions, no parallel solutions. This also means that it cannot be an infinite solutions in the plane. So this limits it to 4 different options now. So now we need to determine whether or not they're coplanar. So we need to calculate n1 cross n2 dotted with n3, or again, whichever order you prefer. Okay, so I'm going to work out the cross product here. The first two, I'm going to write down my numbers off to the side. So I get negative 2 minus negative 3. I get 1 minus negative 1. And I get negative 3 minus 2. I'm going to dot that with 2, 1, and negative 1. Okay, so now I'm going to work out the dot product. 2 plus 2 plus 5. So that equals 9. So notice that's not equal to 0. So the only instance this happens is when we have one solution. So we know that there's only going to be one point of intersection. So let's find that one point of intersection. So now we got to determine by eliminating one of the variables. So let's say I take equation 1 and I take equation 2 and I add them. So 1 plus 2, that's going to give me 2x minus y, no z's, equals 0. And I'm also going to eliminate the variable z from equations 1 and 3. So 1 plus equation 3. You may have to multiply them by something to also eliminate. So that gives me 3x plus 3y equals 9. So now I've got two other equations. I'm going to call them 4 and 5. So what I'm going to do is I'm going to eliminate, in this case, from 4 and 5. Let's eliminate the variable y. So I'm going to take equation 4, I'm going to multiply it by 3, and I'm going to add this to equation 5 that I already have. So this gives me 9x equals 9, so x equals 1. So now that I have x equals 1, I can substitute that back into one of these two equations of 4 and 5 to actually solve for y. So I'm going to substitute it back into equation 4. Again, doesn't matter which one you substitute it into. So I get a y value equal to 2. So now, all you have to do is substitute back into one of the original equations. Let's say equation 1. Oops, what was that equation again? X plus 2y plus z. So x plus 2y plus z was equal to 8, I think. Yes, okay. So 1 plus 2 times 2 plus z equals 8. That equals 5 plus z equals 8. So z equals 3. So there you go. There's my point of intersection. It's 1, 2, 3. Okay, let's see that again with another instance. So again, just by inspection, you can actually look at the normals. I'm not going to write out the normals this time, but you can see the normals are not collinear. The problem actually turns out to be a lot easier if they do turn out to be collinear. And therefore, you can start eliminating some planes. And then it goes back to just looking at how two planes might interact with each other, or something like that. So let's now determine how if these planes are coplanar. Sorry, if the normals are coplanar. So 1, 2, 3. This time I'm going to cross it with 2, -1, 4. And I'm going to dot it with 3, -14, and 1. Okay, so again, I'm going to write off to the side 1, 2, 3, 1, 2, 3, and 2, -1, 4, 2, -1, 4. And I'm going to work out the cross product. So in this case, I get 8 minus -3, 6 minus 4, and -1 minus 4. I'm going to dot this with 3, -14, and 1. Okay, so this is 11, 2, -5, dotted with this vector 3, -14, and 1. So 33 plus, minus 28 minus 5. Well, that does equal 0. So that means these normals are coplanar. Okay, so we still have to go through the process of elimination and substitution to see what kind of options we have available to us. So in this case, I'm going to eliminate the variable x. So to eliminate the variable x, I'm going to take my first equation, I'm going to multiply by -2, and I'm going to add it to my second equation. So -2x minus 4y minus 6z equals -8. Okay, so I get -5y minus 2z equals -15. I'm going to do something similar. I'm going to take equation 1 and multiply by -3 this time. I'm going to add it to equation 3. Okay, so when I add these two, I get -20y plus, minus 8z equals 19. So my two new equations we're going to call 4 and 5. So in equations 4 and 5, I'm going to I'm going to eliminate the variable, let's say y. So I'm going to take equation 4, I'm going to multiply by -4. So I get 20y plus 8z equals 60. I'm going to take equation 5 and add that. So what I find out is I get 0y plus 0z equals 79. Well, based on this expression right here, I can see there are no possible values of x, y, or z. So that gives me the instance that I have no solutions. Only if there are solutions are you required to actually write solutions. If there's no solutions, you just state that you have no solutions. And thus concludes lesson 8.6.